the basic agenda of this presentation is not to give you a detailed description of the dissertation, but rather a quick review of the research questions that we have tried to answer in this dissertation, and also a quick review of the research outcomes that we have achieved during the presentation process. So the most relevant question might be at this point, why this is an interesting topic, and well, we have already experienced, and we are currently experiencing also significant advancement in cloud computing, in Internet of Things, and also with 5G knocking at the door, the more and more processing are actually now moving towards the cloud, which essentially means, in case of cloud, server-based systems in data centers are the key enablers. And in this case, the amount of energy that these systems are using is unprecedented. Let's take an example from the worldwide LHC grid from CERN. This is, by the way, a picture of the LHC experiment, which is, I think, the largest experiment for the physics, particle physics. So this LHC computing grid, it has more than 170 computing centers across 42 countries in the globe. And currently, CERN is using 1.3 terawatt hours of electricity to power these experiments. To put that into context, this amount of energy is enough actually to power 300,000 homes in the United Kingdom for a year. So a bulk of this energy, or a good amount of this energy, is actually used to store and analyze and distribute around 50 petabytes of data, which is expected in 2018. And in October 2017 alone, CERN crossed one of its records that it produced almost 12.3 petabytes of data. So the amount of data that's being generated and analyzed, it is actually producing a lot. It is actually using a lot of energy. And just to give you another quick example, I have taken this slide from last year's ICHPC, where the top 500 supercomputing systems were actually declared. Each year it is done so. So if you see these graphs, this actually shows you the increase in power consumption in the top 10 supercomputing system, and which is around 3x in the last 5 years. And the trend is almost similar for the top 50 or top 500 systems. So we can see from these slides that actually energy consumption in this case of high performance computing is really a big concern nowadays, and it is also taking a large amount of interest in research. So based on this, what we tried to achieve in this thesis is that we actually asked ourselves 3 broad questions. The first question was, how can we accurately measure the energy or the power consumption of computing systems? And the goal here was to find out a tool, a method, or let's say a process which can be cost effective, which is reliable, which is always available, and it gives very negligible overhead. So the next question that we asked is, given that we have such a tool which is giving us accurate accounting of the energy consumption, is it possible to model the power consumption of the computing system? So nowadays, not any such tool is there which can give you a full system power consumption, unless otherwise you are actually using an external power meter. So the goal here is actually to find an accurate prediction of the full system power consumption, given that we have some amount of the power consumption of the CPU and the memory, for example. And the same goes for component level power accounting. Is it possible to somehow break down the power consumption inside the CPU components? And of course, workload specific power draw characteristics will be another interesting thing that we can actually achieve from this. The third question that we ask is that is it possible to analyze and optimize the power management of the computing systems? And the goal here, in this case, we said that if we have a data center log, can we actually understand something about the power consumption behavior of the computing systems? And with such an understanding, it would help us to actually do the energy efficient workload consolidation and also management of resources. So methodology, actually, obviously, what we have done in this dissertation is that we have tried to formulate the problem practically and then designed solutions which were actually tested on a wide gamut of customized benchmarks, synthetic, non-synthetic, and also application benchmarks. We have also written our own benchmark for the power measurements. So what we found from the literature is that Interstrapple is one such tool which can actually give you the power measurements of the system. I am going to introduce Interstrapple in the next few slides, so I'm not going to talk too much about that. Given that Rappel is actually giving us accurate enough information of the energy of power consumption, we have tried to do full system power modeling with Rappel, and also we have done component level power modeling inside the CPU, targeting the instruction decoder. And lastly, we have actually leveraged the logs from CSC, which is the Finnish IT Center for Science, and performed analysis on those data set to obtain interesting insight into the data center power expenditure. We have also performed the analysis on the graph processing platforms, namely Apache Giraffe and Spark's GraphX. So before delving into the brief research outcome, I will just give you a brief overview of what Interstrapple is. It's called running average power limit. The basic idea of Interstrapple was to actually expose the energy consumption of different domains inside the CPUs, okay? And it can also limit the power consumption of those CPU domains. For our case, in this dissertation, we are particularly looking into the energy measurement point of view. So it gives the energy measurements across 5 different domains. So this is the package domain, which actually gives you the power consumption of the entire socket, which includes the core, the uncore, which includes the last level cache and the memory controller, and the on-chip graphics. The power plane 0 gives you the energy consumption of all the core in total. It is not giving you the power consumption of the individual cores. Power plane 1, sorry. Power plane 1 is giving us the information about the energy consumption across the integrated graphics, and DRAM is giving us the energy consumption of the RAM that is attached to the memory controller. Starting from Intel's Skylake, there is a new domain that's introduced, which is actually not available in all the different versions of the Skylake architecture, but then again, the main idea behind PCs is to give the energy consumption of the total system on chip. So I'll briefly go through what are the research outcomes that we have actually discussed in this dissertation. The first of all them is that we have used Rappel to profile application. We have included this energy profiling module in an IGProf, which is a profiler to profile performance and memory. We have added this functionality to also profile the energy, but this was a very basic implementation. The idea was actually to see if Rappel can actually produce, or Rappel can actually show some correlation or accuracy in case of the profiling. And as we can see from this figure, the blue dots were the performance ticks, and the red dots were the energy from the Rappel, the package energy, and the PP0. And these two actually kind of goes along very well and kind of define the profile of the application which was profiled. In this case, it was stream benchmark, and these are the 4 different functions of those benchmarks which were actually profiled. So basic takeaway is that Rappel is accurate enough in this case to kind of profile the energy measurement inside functions of the program. We continued our experiments with Rappel, and what we found out is that when the frequency of the computing system is increased or decreased, the Rappel measurements actually match very well with the external power measurements. This was, in this case, the wall power means the power measured by the external devices. And there was quite a good correlation between them. And as you can see in this case, this is from the parsec benchmark suite, which is a non-synthetic benchmark. And the package power and the wall power actually correlated very highly. But we kind of actually modeled this. There was actually different coefficients in case of the linear regression. So we modeled this and using the least square regression, and we got the lowest error rate in case of the linear regression. The takeaway from this experiment was that Doctoral can be actually used to model the power consumption or the full system power consumption. Next, we actually dealt upon breaking the power consumption inside the CPU components. And in this case, we took the instruction decoder. Our basic idea is that it is in theory it is that the x86-64 instruction set is consumes more energy, and it takes more time to actually decode those instructions. So we leveraged that idea just to see if it is the case, and we used Intel's Haswell architecture for that because it has micro operation cache. And in here actually we are showing two different scenarios, where the first scenario was actually giving you the energy consumption in case where L2 and L3 cache is consuming the highest amount of energy, and in this case the instruction decoder is actually consuming the highest amount of energy in case of the instruction decoder only, not like highest in between the other components. But what we found out is that the instruction decoder in this case is actually consuming between 3 to 10% of the energy, which is not bigger if you compare it with the L2 or L3 cache dynamic consumption, which was 22%. So the basic takeaway from this experiments was that actually it is not true that the complex instruction set is actually, or the instruction decoder is actually responsible for bulk of the energy consumption in case of these systems. Next, we, as I said, we leveraged two data center logs from CSC, and our idea was to do some, again, full system power modeling, and we actually did different types of power modeling on that. First, we tried with linear models. It gave us error rate of 2.1%. That's a mean average percentage error, and but this model actually had also showed some non-linearity, which was not taken into account in the linear model. So we also tried with the Gaussian additive model, and it gave us an error rate of around 1.97%. Another interesting observation on this dataset was that we also had the job status from the dataset, and they had 4 different types of job statuses. So completed, the jobs which are completed and produced successful results. Failed are those jobs which actually failed to produce any useful outcome. Cancelled were those jobs which were cancelled by the users. Most of the time these are also failures, but there are cases where it can actually produce some meaningful results. And timeout, which are those jobs which couldn't finish to completion, and these can produce successful results but cannot. That's what we were told. So if we take a pessimistic approach that all the non-completed jobs are actually failures, what we found out is that 16% of such jobs are actually taking 43.5% or almost 43% of the CPU time. So as we said, this is a pessimistic view, but then again, if we can somehow identify these jobs in the earlier stages, like using machine learning or those kind of technology, then we might actually reduce the consumption of the resources and also the energy. Next, we perform the energy efficiency analysis of graph processing platform. I will just quickly go through this. The two platforms were Apache Giraffe and Spark GraphX, and we performed these experiments on real graph datasets. So these graphs are actually, if we go down, the size of these datasets actually increased. And we implemented 3 different algorithms: PageRank, single source shortest path, and strongly connected components. So the thing that we saw in case of PageRank is that GraphX was consistently taking less energy and less time if we compare it with Giraffe. But when we actually go on with different algorithms, we saw that there were also situations where both of them had comparable finishing time, and there are some cases where Giraffe was actually taking less energy, than graphics, although it was completing it was taking a bit more time to completion. And of course, there were also cases where Spark couldn't actually finish the completion. There are quite a good number of reasons for that, because Spark uses memory, and the memory can run out pretty quickly if the iteration count is too high. We have included quite a few observations on that and how to mitigate some of these problems in the presentation. And lastly, we actually performed a rigorous evaluation of RUFL as a tool. We have used different types of systems like workstations, server, and also we have performed experiments on Amazon EC2. We have used Intel's Sandy Bridge, Haswell, and Skylake architecture for that. What we found out is that in case of accuracy, it can actually correlate pretty well with the AC power. The plug power estimation capability of RUPL was very good, and the error rate was within acceptable limit. There were actually high correlations in case of Haswell, which has been improved in case of Skylake, and the correlation has now been reduced. The sampling rate of RUPL was 1 millisecond previously, but what we found out with the newest version of Skylake, it has improved the sampling rate in case of PP0, which is only 50 microseconds. There was negligible performance overhead with RUPL, only less than 1% in case of standalone system, and less than 2.5% for the Amazon EC2. The DRAM energy measurements or this evaluation was not performed by us, but I'm just putting it here to make it into the context, is that it shows less than 20% deviation from actual measurements, depending on the architecture. So the good things that we actually noticed about RUPL is that it has high accuracy, it has negligible performance overhead, it has high sampling rate, it is always running, and there is measurable correlation with temperature. But when we look into the bad or weaker aspects of RUPL, we found out that it is not still capable to deal with the register overflows. There are non-atomic register updates. That means that these 4 different domains that I saw, package PP0, PP1, and DRAM, they do not update atomically. There were significant, well, I wouldn't say significant, but DRAM energy accuracy has improved, but then there are, as I said, deviation across different architectures. And individual core measurement is not supported, and also there is fixed sampling rate. So, basically, how can we improve these things? For example, the profiling tool that we have shown, it can be actually extended to profile per job energy spending for software applications. We can also expand the power modeling techniques to diversified workloads, because we have mostly focused on CPU intensive and memory intensive workloads. So it can be extended to go beyond also the Intel architecture, because AMD also has similar MSRs, for example. So, and we can also obtain detailed power modeling breakdown of different components of the system, not only with the CPU that we have shown, but we can also obtain the power consumption breakdown inside different components. And of course, we can improve these techniques to perform energy efficient scheduling of workloads in HPC. I think that's